Okay, so for our elementary statistics series, this is video 4, and I would say now we finally get into the class. So we did a few introductory videos, not so important. So in the beginning, throughout the course, we will have definitions, but it's a big part of statistics. So if we wanted kind of a very clear opinion, this is where the course starts. Now, this is an elementary statistics course from beginning to end. We just want to be as comprehensive as we possibly can. Yeah, so a class, an entire course is a textbook, and if you go front to back through a textbook, it's an entire class. So a textbook is a class, of course. This online course is just meant to simply be an entire stats course from beginning to end. We do concepts, then we go into the next, and we go into the next. So we want to kind of start by defining a few things. We did this in the last video, but I just want to be clear here, so we'll do it now. And as we go to, problem 11, problem 12, we're going to go deeper into the definitions. So this, with question 10 starts the statistics course. Let me just repeat what we did at the end of the last video so that we start here. We're going to define statistic and parameter. So that's what we're going to define there. Yeah. So as we said, population size is capital N. We call that population. And you have a population usually very large. There's not rules. We don't want to talk about that now. Doesn't matter if it's 3,000 or 3 million or what it is. Whatever the population of study is usually fairly large. From that, describing the random sample, which comes later, is fairly difficult. Actually in real life, collecting a random sample, it's not the easiest thing to do. But assuming you can collect a simple random sample, as we say, it comes later, we collect a simple, random sample. Yeah, not math. It's very, very annoying to say all these definitions. If we can collect a simple random sample, we collect a sample from the population, and that's sample size n, little n, which is very common throughout the entire course. That's going to be sample size. N is sample size. Yeah. So that's going to be a sample, which obviously is collected from the population. Okay, so I don't want to get too sidetracked, but in simple terms, a parameter, we're supposed to, what are we doing here? A few things always. I can't really stay clearly on point. We're doing always a few things at once, but mainly what we're trying to do is to define parameter and sample. We're defining parameter and we're defining statistic. Okay, so if we put it simple, a parameter is any value, any numerical value that describes a population. A statistic is any numerical value which describes a sample. It's supposed to be an arrow. So what are some examples? So mean, yeah, mu, its Greek symbol mu, like a cat, that's population mean. What does sample mean? It's x barred, yeah. And capital N is a parameter. It describes a population. Lowercase n is a statistic. It describes a sample. Okay, so what about standard deviation? It's Greek symbol sigma. That's not an R. That's Greek symbol sigma is a population standard deviation. Why not an S? Because S is sample standard deviation. Yeah. So there's a proportion. A proportion is exactly that, a proportion. You have an entire population, 30% have blue eyes. That's a proportion. So P, keep it simple. Population proportion is P, yeah, whereas sample proportion is P hat. Yeah, so all of these are numerical values describing a sample, therefore they are a statistic. All of these are numerical values describing a population, therefore they are parameters. So it's as simple as that. We'll try not to repeat this too much in future videos. We'll see what happens. More than I can possibly remember off the top of my head, yeah. So here's one. This is, we just don't want to define this that well now, but it will come later in the class. R is correlation coefficient. A scatter plot, it's basically a measure of how well a scatter plot fits a straight line, but R is correlation coefficient sample. It looks like a P, but Greek symbol rho, RHO or something like that. That's the population parameter for correlation coefficient. So you have more than I can ever remember all at once. There's a lot, but there's the most common all the way to ones that you don't see very often. I guess we would say most important, is a mean standard deviation and proportion, mean standard deviation, or proportion. But if they kind of give a general statement, people have difficulty, read a paragraph, okay, good, but how do I know a population parameter or a sample statistic? Well, even after, a few months or a couple semesters, it can be hard to know. It depends on how easy they make it for you, yes. But usually if they make a general statement, they just say something generally, there's always kind of a cheat. This is not the only thing I'm going to say. If they make like a, kind of a general statement, whenever they make kind of a general statement, that usually means that it's a population parameter. Yeah, whenever they just kind of generally state something. Now, it's a lot easier with sample because usually this is not always true, but usually they say sample size n. I'm looking for a sample size n. We're reading a sentence. If they say sample size n and then they talk about a mean and a standard deviation, usually it's talking about the n from which it came. So usually it's pretty obvious if something is a sample. We get a sample statistic, we get more confused about population parameter. But if there's no n on the page, usually it's a population parameter. So we do have a few hints along the way. We can read this, but there it is. So this is a different definition. Determine whether the data described below are qualitative or quantitative. So very, very important and very easy in stats. I think everybody knows this. Quantitative, qualitative. Yeah. So this is numerical. Quantitative can split into different categories here. Yes, but any number or numerical, it is a definition, so I don't want to mess up and accidentally give you a technically wrong definition. Yeah, numerical. But yes, basically quantitative and numerical more or less are the same word. It's not like they're similar, they're more or less the same. But a quantitative or a quantity does have to be a number. I know it's just saying the obvious, but that's the definition. If something is not a number, it cannot be quantitative, and quantitative does mean it's a number. So quantitative does mean numerical, integers, decimals. Later in a minute, like literally right after this, we're going to talk about discrete or continuous. It doesn't matter the kind of number, both discrete numbers and continuous numbers are numerical or quantitative, but quantitative literally just means it has to be a number. So we don't have to talk about this. We know that qualitative is a quality. Qualitative is simply a quality. Yeah. And it's like eye color, car color. There's many, many obvious examples, but whenever we have to think of one off the top of our head, we kind of we kind of get a little lost for words or something. But qualitative is just a quality, not numerical. But I guess usually in math you want to split things into sets. We want to very obviously be able to split things into sets if we can. Yeah. And we have confusion. I still get a little bit confused. It may or may not come in the class, but you have like jersey numbers. Yeah. So we have a football team or something, and you have jersey numbers. Jersey numbers, you have special cases because jersey numbers are numbers, they're quantitative. Yeah. But it's one of those things where it's more often considered, qualitative or something. Let's just not make a big comment. But if the ordering from least to greatest of jersey numbers has no meaning, then it's more of a quality that describes a person. So jersey numbers are not quantitative, they're qualitative. Yeah, you have things like that. The number of students, blah, blah, blah. We don't even have to read the question. It's quantitative because their measurements are numbers. Okay, so now we want to talk about continuous and discrete. So let's kind of do this a little bit better than I did before. We have quantitative, I have to say it right. We have quant, and we'll just kind of scratch this off because we don't need it. but we have qualitative, yeah, which is a quality. So we know that quantitative simply means numerical. Yeah. So quantitative is going to be a numerical value. Now, typically, yes, I think it branches off to two and only two categories. Quantitative, if you have measurements or results or data collection, which is quantitative, there's only two. They're going to be discrete or they're going to be continuous. Okay, so I find it a little bit better to discuss continuous. So there will always be one or two rule breakers, not really a rule breaker, but when we generalize, it's good because if we generalize, we literally cover 95 to 100%, 95 to 100% of possible examples. I wouldn't say exceptions, there are none, but ambiguities we might not cover. Yeah, but this is true. Yeah, this is true. Every continuous number, anything which is continuous is a measurement. It's kind of the way that I describe it is a little bit weird, but not really because it's true. Yeah. Any measurement, that's it. A measurement is continuous, and a continuous quantity is a measurement. They go hand in hand, so that's it. Any volume, milliliters, is continuous. Our weight, yeah, our weight is actually force in newtons or pounds or something. Yeah, our weight or our mass in grams or kilograms. Our height, you know, I don't always write on this thing very good, but we're talking about it. So we can go on and on, but a continuous random variable is automatically a measurement and all measurements are continuous. Now, continuous does mean infinitely many values. It does mean infinitely many values. What goes with a measurement? Yeah, snowfall, rainfall, all of it. If it's any kind of a measurement with units, it's continuous. So that's all we really have to know. We don't have to understand the definition of continuous very well. Yeah. But anything that's continuous, any measurement, even if we don't write it, it comes with a number line. Yeah, not necessarily negative. Uh, in reality, no negative because it's blah blah blah. After this, we're going to do interval and things like that. You have temperature scales that do have negative. It's just realistically with measurements, you can only have positive numbers. Yes. But we know that the number line has infinitely many values in there. Yeah, even if we cut it off, people say, wait, but we cut it off at 2, 3 decimals. There are many, many possibilities, but not infinite. We're talking about the concept. All continuous or all measuring systems are all on a number line, and there are infinitely many values for continuous. Continuous does straight up mean infinitely many values. That's what it means. If we understand it a little bit more conceptually, that's fine, but all a continuous random variable is a measurement, so it doesn't matter. Now, we don't need this here. This comes later. This is kind of a very bad sketch of a normal distribution, which is continuous always, not sometimes always. Yeah, a normal distribution. So all continuous random variables, all continuous, they have distributions that look like this, unlike discrete, which are always an xp of x. Discrete are always an xp of x, which is a completely different look. But when we have these shadings under a graph, it's always a continuous random variable. So we should understand what things are, but in the beginning, there are certain characteristics that we can memorize, and we just automatically know what it is. Yeah, so continuous is measuring system, and there are infinitely many values for continuous. Okay, so discrete, which is another word for finite, sometimes they have discrete math or finite math, more or less the same class. Yeah, so finite just means we can't say the opposite of infinite, but finite means it's not infinite, yeah. So they're not exceptions or anything. I'm just saying discrete is usually integers. What is example of discrete? Counting the number of people in a restaurant. Yeah, people get confused. There's 3 people in a restaurant, there's 40, 3 people, 40, 101, 27. Well, they say, well, integers can go on to infinity. It doesn't have much, the fact that integers can be counted to infinity doesn't have much to do with the concept. Whenever we're naming an integer number of people, and these are not measurements, discrete is counting things, counting the number of anything, counting the number of people in a restaurant, try and come up with some creative ones, but it's hard, but counting the number of people in the stadium, It doesn't matter how big the number is, counting things is discrete. So we could just say that counting. And are there exceptions? No, we don't say exceptions. What we prefer to say is some unusual things. But discrete is counting, which is finite. And these are all quantitative. Yeah. But these have distributions, like I just said a moment ago, in the form x, p of x. This comes later, discrete probability distribution. But the values are numbered 0, 1, 2, 3 to whatever n is, and then you have the probability of each value. But they don't get a shading, they get things like that. Now, we don't say exceptions. Usually money is oftentimes continuous. You know, people have difficulty understanding time is continuous. Yeah, so time is specifically a continuous variable. It's a measuring system, time. Yeah, but we'll kind of move on because I'm kind of rambling now. But shoe size, I just want to kind of give something here. Yeah, there'll be countless examples that I'm not thinking of. Yeah, but shoe size is often, 10, 10.5, 11, 11.5. So shoe size is not always an integer, obviously, but it's not continuous. Basically, if it's not continuous, it's always discrete. Is there a third category? The answer is no. Everything in statistics is continuous or discrete. And there are many little ways of looking at it like that. Continuous is a measuring system. Sometimes I just ask myself the obvious question, is it a measuring system? If the answer is no, it's automatically, you know, a discrete variable. Of course, not that we made a mistake, we didn't, but I didn't do it on purpose, but I just said something very difficult, didn't I? A shoe size is a measuring system, isn't it? But it's not the kind that we're looking for. A shoe size is discrete. But we see the point, even though shoe size are not integer values, 10, 10.5, 11, 11.5, there's still a finite number that you can have, so it's considered discrete. So what do we have? We have quantitative and we have qualitative. Qualitative is a quantity, and then quantitative is further, they're going to do after this nominal, ratio, and levels of measurement. The quantitative is going to be broken down into discrete or continuous, yes. So blah, 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 state whether it's discrete or continuous. The number of computers, they just said it. Obviously, if we know me, I don't take the time to read a lot of stuff. The number of computers means we're counting something. Yeah, the number of computers in a room is obviously discrete. Okay, good. So it goes on from there. What do we do in this lecture here? You just want to stop when it's kind of prudent. But we did parameters. We're not trying to review. I'm just saying in this video, we did parameters and statistics, which are sample. Yeah. And then after that, we did quantitative, qualitative. We're not going to put qualitative with statistics. It looks like I'm categorizing these things certain ways, which I'm not. But we're starting to kind of get into the meat of it now. So we said quant, and we said qualitative. And then what did we do with this? I'm just trying not to cover up the question. We said a discrete, and we said a continuous, random variable, which is a measuring system. Yeah. Okay, so they further kind of break this down. Yeah, and it gets hard because it's not like quantitative within this world. Really just probably only nominal. Yeah, so we want to do a little bit better of a job. Within this world, they do have qualitative. I think, I don't want to make a mistake. I think the only qualitative is nominal. I don't like to say exceptions. It's more like things that we haven't mentioned. But if we categorize these in certain ways, I'm very, very happy if you refer to my YouTube channel because we kind of go through this systematically just for fun. But any basic thing I say, you can Google image. Don't be afraid to use Google image. You can Google image a nice pretty chart that's honestly better than what I give you. But let's see if we can make the full thing right now. Let's try and do this. So we have quantitative. We have qualitative, which is a quality. So I haven't talked about this. There will be stuff that we leave out, but we'll cover all the basics. Yeah. These are levels of measurement. What is this here? Levels of measurement. This whole page here is levels of measurement. Yes, I think that there's only four. Yeah. Okay, so the lowest, and well, we're not going to think quantitative or qualitative. I wrote those, so we don't erase them, but we're going to come back to that. Right now we're in the middle of the page, yeah. So the lowest form, the lowest level of measurement is nominal. I really exaggerate too much talking about things that are way too simple. It's written right there. I just don't always feel like spelling things. Um, Nominal. Okay. So nominal is just information that cannot be ordered. So any data that can't be ordered, yeah, any data that cannot be ordered is nominal data. Yeah. So eye color cannot be ordered. You can list it any way that you want. If they're trying to rank something in some weird way, it's automatically ordinal, which we'll talk about next. They take something and say, oh, wait, but for this study we can. Well, then it's graduated up to a different level of measurement or something. But any data that cannot be ordered is going to be nominal data. So that's it. So if you can't order stuff like eye color, things like that, if it's impossible to order it, it's going to be nominal. So the lowest level of measurement is going to be nominal, and it's just information that we can't order. That's nom. And then it goes from there. Just to say it, the lowest is nominal, and then there's ordinal, and then there's interval, and then there's ratio, which we like. Yeah. Let me just think about this for 1 second. Yeah, so I had just paused it there and I was kind of thinking about the thing. But obviously we just have kind of a generic, picture here off of Google. Like I said, if you ever want something, just as good as my videos, just Google image uh, level of measurement. What are these things? They are levels of measurement. So you Google image level of measurement is what you do. But there's kind of a twist and turn and not really. Um, but we see that we have a qualitative, yeah, and we have quantitative. Quantitative is also numerical. What we had not mentioned is categorical. Yeah, categories are always going to be qualitative. So a category is qualitative. We see the little bits that we forget there, yeah. And then so from low to high, yeah, these are the level of measurements. I'll take my own notes. So nominal is information that cannot be arranged, and that's of course qualitative, categorical. Ordinal is information that can be arranged, and that is usually also qualitative and categorical. We'll do this a little bit better on the side. So then interval and ratio are very similar. Basically, interval and ratio, I'm not allowed to say the same. They actually are, but there could be disagreement. But interval and ratio are both, infinitely many values on a number line, except interval contains negative numbers, ratio does not. So we talk about some common things here. Okay, so nominal, we just kind of skip. Anything that we cannot order or rank is going to be nominal. So nominal. So ordinal is much more affiliated with qualitative or categorical. Ordinal means can be ordered. So ordinal means it can, just a little redundant, can be ordered, yeah. But what is an example? So like, if we're grading the professor at the end of a class or something, and, or, that's kind of bad, maybe grading a website or somebody's service, they have low or something to medium, low to medium to okay to high, and you have to like rank their things. So one way that they say ordinal is you order things from least to greatest where there's no clear, distance between. If there's no clear distance between, um, it's going to be ordinal. But ranks in the military, yeah, that's the rankings is ordinal data. Rankings in a military, I don't really know that very well, so we can't use it, but it's one of the most common examples is what do they call that in the military and other places? Hierarchical, blah, 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 whatever that thing is. But those are going to be ordinal data. So ordering things that can be ordered without basically almost always no numbers, but at least no clear numbers. Okay, so if we have a scale, yeah, that has negative numbers, -1, -2, it has positive numbers, 2, 3, 4. So this is kind of the weird thing here. Let's be careful here because a discrete, so this is one of the reasons why I turned to this, because discrete really messes with us here. Yeah, what is discrete data? Discrete data, is it going to be ordinal discrete data? I mean, it is quantitative, or is it going to be interval, discrete data? Yeah, so it's hard to make a comment on the discrete data right here. Let's just kind of come back to that idea. But the thing about it is for the most part, in my head, interval and ratio are all continuous. Yeah, they're quantitative, they're numerical, but they're continuous, which I just said previously means some sort of a measurement. So the thing about all measurements, I know that temperature is an example. Yeah, all measurements are going to be positive numbers. Uh, I wasn't able to say it because I interrupted myself. But if you have any scale, if you have any continuous number line here that does include negative numbers, it's interval. That is specifically the definition and the difference between. So if we have a scale which includes negative numbers, it's interval. This is interval. If we cut off the negative values, in real life, time cannot be negative. Time is a ratio. Most measurements are ratio. If you start only at 0 up, all we have are 0, 1, all the infinitely 1.23s, find infinitely many values. If we have a scale 0 and beyond, then it is going to be a ratio. That's what ratio is infinitely many values, 0 higher. So what is ratio? Uh, Basically, we're not going to say a temperature that's interval. Ratio is basically any value that's 0 or higher. So time, all measurements, weight, yeah. Ratio and continuous are almost always interchangeable. Yeah. Continuous or random variable. But here's the Kelvin scale. We never get this specific. Yeah, the Kelvin temperature scale is an absolute scale. It starts at 0 and it goes up. Usually temperature is interval. Yeah, so Celsius, and it's really weird because it's the same thing, Celsius or centigrade or Fahrenheit. Yeah, because they have negative numbers, they consider it to be interval. So that is kind of the basic thing there. Let's kind of pause here for just a second.